Okay, we now return to what I've referred to a couple of times as my favorite shape. The one I've been using, I guess, it has the top curve is y equals ln x. I don't mean to imply it's the only curve I could ever use on top, but basically the thing about this shape is that it's just lines on three sides, but then it's a curve on one side that allows me to introduce this corner, which shows us a particular complication in setting up these integrals and how to deal with it. So what we want to do is we want to take this region and revolve it around the line at y equals -3. We want to do it in two ways for comparison. We want to do it by the washer method and the shell method. So hopefully you still remember the washer method. So let's set that up. What we can easily see is that we have here on top, we have the top curve, and we have the green curve is the bottom curve. Write that a little neater. So what we get when we do this by the washer method is we're going to get washers that look more or less like this. Let's use different colors so you can see the washer. Usually I know I make the red one the inner one, but so here I have a washer that's defined by the outer radius minus the inner radius. So if you remember how to do this, we set up a washer integral. I don't want to review the washer method. You'll have to go back and review that if you don't remember it. But we take pi times the integral of, and we need the outer radius, which is going to be the distance from the top curve down to the axis. So that's going to be ln x minus -3 squared, and then we subtract from that the bottom curve, which is -1 minus -3. The bottom curve minus the axis, we square that and just put a dx after it, and that gives us the volume of this region by the washer method. So let me just annotate what all of these are. So this is the outer curve. This is the axis of revolution. This is the inner curve. I know it's not a curve, I know it's a line, get used to it. And this is the axis of revolution. Oh, and then, sorry, I forgot to put in the limits of integration. We go from the lowest possible x value to the highest possible x value, which is 2 to 3, and we put a pi in front of it because these are all based on the area of these circles, and that gives us the volume of revolution. Okay, so there's part A. Let's set up the same integral by the shell method. I don't know what happened to my L there. That was ln x. Okay, so B, the shell method. So when we use the shell method, look what we're going to be doing. We're going to take a shell. There's the side of the shell. And we know that since it's a horizontal axis, our shell is on its side. So it's going to look kind of like that. So let's see what the dimensions of this shell are. For one thing, there's the x-axis and there's the y-axis. Here's some arbitrary point y, and what we know is that the distance between y and the axis of revolution is just going to be that. So it's going to be y minus -3, or we could write y plus 3, and that gives us the radius of the cylinder, because here's our cylinder, and we can see is that the radius is just going to be that vertical distance there, so from y down to -3. Now we need the quote height of the shell, where the height of the shell is just going to be the distance between the right curve and the left curve. We can see that over here that horizontal line intersects the line x equals 3 on the right and x equals 2 on the left, so the height is just going to equal 3 minus 2, or just 1. It's a constant of 1. But as you know from the previous examples, it's not a constant of 1 everywhere. It's only a constant of 1 up to this line. Once we get up to that line, if I draw another horizontal line through the region, now I intersect the same curve, x equals 3 on the right, but I intersect this purple curve, y equals ln x on the left. So let's do the first part of the integral. First part of the integral, we'll set up just the bottom part, is 2 pi times the integral of, we need the radius, Remember that a shell integral is going to be radius times height times thickness. So the radius, and we have the height, which is just 1. In fact, I'll write it so that you can actually see where it comes from. It's just 3 minus 2, the curve x equals 3 and x equals 2, and dy. And we do that from a low value. The low value in this region comes from there. It's this green line, so y equals -1, up to, sorry, not that, yes, actually that line. This line, which is going to be y equals ln2. How do we know it's ln2? Because that point of intersection is going to be, we know the x part is 2, we plug it into the curve and get ln2 as the y value. So this is going to be 2 pi -1 up to ln2. But we're not done because we have to do the top part of that region. Recall from the earlier example that y equals ln x is the same curve as x equals e to the y. So that's the left curve looking at this sort of pale green line that intersects the two curves. We can see that on the left it intersects the x equals e to the y curve, which is the same as y equals ln x, and on the right it intersects the vertical line x equals 3. So we're going to add another integral that goes from y equals ln2 up to this point, which by the way is, recall that this point is 3 ln3. So that's the line y equals ln3. So we're going to integrate from ln2 up to ln3, and then we need the radius again. The radius function doesn't change because I can simply put a different point y all the way up here, and the vertical distance from that point down to y equals -3 is still going to be y plus 3. Oops, let's do this. And so that's the radius. Then I put in the radius of the cylinder. Then I put in the height, which is 3 minus e to the y. So that's just right minus left for this region up here, and then dy. So there is our solution in shells. Why do we do something that complicated? Basically just to show that we can. That's the whole point, is to understand how to set up these integrals based on the geometry. And by the way, I just want to draw in here what a cylinder up in the top region might look like. See, it's basically the same thing. It's just going to be a much bigger cylinder like that. There we go. And of course, I forgot to put in here that this thickness is, of course, dy. Okay, so there's another example with my favorite shape.